Hello and welcome to 17th lecture of course on corrosion, environmental degradation and surface engineering. In previous lecture we started testing requirements. We highlighted the importance of testing and required data to be fed to the software also when we do a modeling, because everything cannot be tested and we need to get optimization after doing some sort of test, but a lot of modeling in this case. But testing is important, and then we classify testing in two categories. We say destructive testing and non-destructive testing. In non-destructive testing, we highlighted 9 techniques. So, that was slightly kind of the overview in previous lecture, but we will be covering one technique in detail and then some sort of merits and demerits relation. Moreover, how do we really go ahead to choose which technique should be selected. So, that kind of overview will be given, and of course, we will continue lecture 18 also on NDT or maybe say non-destructive testing. So, what was mentioned in previous lecture, we say NDT plays crucial role in quality assurance, because we want better and better quality, safety and preventive maintenance. We say it can be one of the very strong maintenance strategy. Based on the data, whatever we get, we can really frame preventive maintenance policy. And then reason being that why we were being given more emphasis on the maintenance, we want early detection of the faults. So, you do not have to wait for the final failure. If you are able to get early sign of the failure, we can mitigate those failures, or we can take a necessary or corrective actions for that. So, that is why we want early signs, so that the catastrophic failure can be avoided. And another thing we can say the maximizing, or maybe we can enhance the life cycle of those system components and materials. Again, as I mentioned, the NDT, whatever we have mentioned, around 9 techniques, but and then there may be many more, because research is still on. Many new technique keep coming, new principles and new achievements through this kind of techniques are possible. As I mentioned in my previous lecture, research is happening to replace destructive testing with a non-destructive technique. So, that will really help society in a big way. However, as I mentioned, that the NDT is a collection of the techniques, not necessarily we have to use only one technique. We may require a combination of technique to get a right solution. So, that is why I say NDT is a collection of technique to evaluate quality of the material, components and system without changing or damaging performance or integrity of the system. So, that is why it is really required, and we know very well that visual testing has been done for the years and years. The people have been gauging fault just by looking at that, or maybe feel that they use a finger and then figure out what is the surface roughness or what kind of the features this surface will have. So, they also use a visual testing, but in this situation we will also try to incorporate some advanced technique. We will try to connect advanced technique with the visual testing. So, that is why we say that during visual testing, inspector or whoever is examining the surface searches the flaws which are obvious, or maybe the thought over that the surface roughness is obvious flaw, or maybe there is some sort of other irregularities. We know the sharp corners will be there. We want to just check sharp corners with the fingers. So, that is also possible. So, this is what we say, the irregularities in the materials or flaw, and it can be done through the visual inspection. We do not really require special techniques for that. However, if there is some sort of flaw and slightly in depth, maybe say that slightly deeper, so top we will not be able to figure out. So, that is why we require some sort of liquid penetrator testing or magnetic particle testing. So, this we say the PT and MT. What they have a slightly different principle. We use a fluorescent liquid or maybe say liquid dye to test the surfaces of having the surface which are having the crevices. So, we will try to figure out what is the depth of that and then the flaw as such. While coming to the magnetic particle, instead of this liquid test, or maybe say liquid dye or fluorescent liquid, we use some sort of iron particles. So, this technique has to be utilized only for ferromagnetic material, it cannot be utilized for other materials. So, in magnetic particle testing, we detect the surface and near surface defects in ferromagnetic materials. So, in liquid test, we look at only the surface, while in case of MT or maybe say magnetic particles testing, we can also look at some sort of subsurface cracks also. Reason being that when the magnetic field and there is some sort of discontinuity, then there will be there will not be a continuous chain of the particle, there will be more like cluster formation, because what is a broken inside the material of ferromagnetic material, there will be a lot of accumulation of the particle, because it will be many places, it will be north south pole will be divided, it will not be in the sequential. So, that is where we can really detect also some sort of a near surface defect using the MT. So, in this case what I can write, that particle or dye tend to cluster in defect zone. So, they get accumulated. Similarly, when you use dye, it will get accumulated at one portion, and you can see there is some depth inside, that is why there is some sort of accumulation. Similarly, particles also they get accumulated or clustered around some defect, maybe then we know that there is some sort of depth in that also. Coming to the other testing, where we can really look at the subsurface cracks, or maybe say through and through complete surfaces. So, we have ultrasonic test, we have radiographic test, we have also that electromagnetic induction technique, and we have infrared thermal measurements. So, in this present lecture, we will be covering more about UT, that is ultrasonic test, which is basically a high frequency test. We will be detailing about that. Coming to the radiographic test, we use generally the radiation, it can be a gamma radiation, it can be X-ray radiation, and then we try to figure out what is the drawback or what are the discontinuities interior of the substance, and we try to capture those using some sort of digitization, or maybe we can really take a photograph in those faults. And then coming to the electromagnetic induction, or what we say the eddy current testing, we can also find the defects, reason being that they are very sensitive towards the discontinuity. We will figure out what will be the depth as such. Now, depends on what kind of sensor we are using, what kind of sensitivity of the sensor we are choosing, that will be important. We can also know that the temperature follows some pattern, and if there is a thermal conductivity of the material, and the material is a crack or maybe having some sort of discontinuity, naturally thermal conductivity will not be there, a temperature will drop there. So, that is where we can look at that pattern of the temperature or a heat, and can figure out maybe there is some sort of discontinuity, there is some sort of flaw in this case. So, again we emphasize that not a single technique will be foolproof, complete, and we should use a couple of techniques to really assure whatever we are judging is correct, and then it will really give a right solution to us. Now, we will start with the visual testing, which is one of the very common technique, and almost everybody is familiar. Just in the few sentences on that, we say that when we think about a visual inspection, one is excellent lighting is important, and we should have a clear vision also. Now, clear vision can come also with a magnification, it can be 3x, it can be 5x, it can be 1000 also. So, we really require some sort of magnification device, and it has been shown in this case that this angle or maybe the angle of this light beam is roughly 5 to 45 degree, which is ideal to get the results. And then here the person is able to look at from a naked eye, that is why we say we require a clear vision. If there is a blurred vision or something, then this will not give a right solution. That is why we say to get a good results, or maybe the result which is acceptable, we require excellent light, we require clear vision, and we require some sort of magnification. Now, as I mentioned that visual inspection, it needs to be many times it is required some sort of support of other techniques, and then it can be as I said magnifier, or maybe the magnification, or some sort of addition to this. And then there are something like here one person is looking at the video scope, That means we are not really reaching to that surface, we do not want to see, when we are not able to see that surface, but we can use some sort of video scope and then figure out what is really happening. And then that is why it has been written that there are some additional which are really required for the visual testing. The borescope is a one, fibroscope, videoscope as has been shown in this, and sometimes we use also CCTV, and this is in these days very common because we can do a remote monitoring also, and it is very common in a very big industries and buildings where we are not able to reach directly, but we want to really see, and then that is where we use CCTVs. So, this is what we say that these are the examples of remote VT techniques. So, visual technique has been known, but now we keep adding more and more features, so that it becomes more and more useful to us. That is why we say the example of remote VT technique to investigate the location where human access is limited, a person cannot really reach, and there is a long pipe, a person cannot really go inside a pipe and try to figure out, and there is a video scope or maybe some sort of camera inside fixed, and it is really telecasting the complete the images of those that circuit, or maybe say that place, or that providing that local information, it will be very important for us. So, that is what have been shown. A video scope can be used for the visual inspection, like in we have given example of tubes, pipelines, even in the welds also it can be utilized, and it can really give a good results, even the number of forging where we, and that is happening inside a surface, and we will be able to get a good results. Now, ASME also provides some sort of codes and then or classification of the visual testing. They say one with a normal visual testing is a VT1, while coming to a VT2, they generally go ahead with a pressurized boundary where there is a liquid, and there is a liquid is the pressurized one. So, say that VT2 category is a visually inspecting pressure boundary of fluid containing system. Reason to locate the leakage wherever there is a leakage in this. So, it will be useful particularly for in service situation, or visual inspection is important there. Even they do some sort of functional testing, or really the unit is pressurized, and then we are able to find out from where the leak is really happening. So, this is a leak test can be done that way, it can be bubble test, it can be leak test, or it can be soap test, and moreover then we can really pressurize a unit, and there will be a hydrostatic test also. So, this is where we say the visual tests are very important, and reason is that we say that there are numerous advantages of using visual testing. In fact, whatever we do, finally visual test also be along with that, will be attached to that. So, there are numerous advantages of using visual testing, and the person who is really inspecting it only requires the skills, or maybe the training, or maybe the experience, if he or she can access the surface immediately. So, more and more experience, more and more technical know-how, the person or concerned person will be able to judge the surface easily. Otherwise, he or she will be requiring a lot of softwares and a lot of interpretation to judge it. So, this is very important, the visual testing, it will really and then is important, and then if we have a skilled person who can really assess, or we can have a good knowledge to figure out what is really wrong with a surface, then the skilled person can do that. Now, if this technique does not really require very specialized equipment, most of the time, so like even the CCTV is a common technique now, a common unit. So, it does not really require a specialized equipment, or maybe even the consumables. It is they are not consuming anything, we are not making any special specimen, we are not really throwing any the sensors or units as such. More or less everything is like permanent or long term. So, that is why we say that as there is no specialized equipment or consumable, visual inspection is one of the most cost effective method. So, if I think from a cost point of view, visual examination with the addition of one or two things like a magnification, or maybe some sort of remote access or something like that, that visual this technique will turn out to be very useful in this case. Now, There is another one good thing about visual examination is that we can take a really photograph, we can really take videos also. Now, videos and photograph can be kept for the future references. It is basically kind of record to us also. So, this is a very important, and moreover now this is important, but however we can say there is only one maybe the major drawback is the expertization. They say that and the reliance of visual examination is basically on expertization of the person who is really examining it. So, that is one of the major drawback, and then if we can automate everything, and it will be very good, but as we know very well that there are so many, there are numerous factors, complete automation will be very difficult. So, we really require expertise, we require skills, or we require really good experience to utilize a visual inspection. If we do not have that kind of information, then VT will not be very useful to us. However, as per my understanding, a person does not have good knowledge, not any single technique will be very useful to him or her. So, knowledge is important, science is important, understanding is important. That is why this course is important from that point of view. Now, let us start with the first technique. I mean, I say that the visual testing was a kind of common testing. Well, another testing what we say the ultrasonic testing. Ultrasonic testing is basically, we know very well that human power hearing power generally varies from 20 hertz to 20 kilohertz. While we are talking in this testing is something like this, where the power goes to the 20 kilohertz to 1 megahertz. However, in recent technique they have mentioned it can go to the gigahertz also. We do not have a restriction on upper limit. Now, there is a need that it can go on a higher side also. Now, they basically send some sort of waves, and they try to transmit the wave, or they retract back, so that we get a purposeful good solution. That is why we say that ultrasonic waves spread linearly until they hit the barrier. This barrier can be now interface between the two surfaces, maybe coating surface and subsurface also, or maybe the flaw as such, maybe crack, maybe the linear crack, perpendicular crack, or maybe oblique crack, or maybe some sort of volumetric void, or maybe there is some sort of void, or some sort of discontinuity in this, or maybe when we say that substance is there, and then there is some sort of grain boundary mixed with a flaw also, there is a possibility. So, wherever there is a discontinuity, there is a barrier, there is no smooth transmission happening. So, that what will happen, it will change the behavior, the ultrasonic waves will change the behavior. So, whenever this happens, some wave will get reflected back, some will get transmitted, some will get reflected back. Now, we can have two different kind of sensor. One is really taking only the transmission, other one is taking the reflected waves. So, we can have both. So, we will be explaining both in this lecture. We say that some of the wave is reflected back towards the interface from where the source is located, and while rest of the wave travel onward through the media. That means, there will be passing through the maybe we have opposite and some sort of sensor that can receive the signal, or maybe if you do not have, it will get transmitted. So, this is important from that point of view. We can have two major techniques as such, because there is a ultrasonic waves, and then we are transmitting to the surface. If there is a surface, there is some sort of flaw, then the waves will get reflected. It may be partial, maybe fully, or maybe transmitted fully or partially, depends on the surface orientation of the flaw. So, that is a possible, and we know that there is a discontinuity, something is wrong, something is need to be looked into that. And if we have a good know-how, we can convert, we can really reproduce that kind of a fault, and we can show what is really inside the surface. Now, this is what we say that if we get a waves either transmitted or reflected, we can get information. Such information is like existence of fault. It can have information on the material thickness, and material thickness has been shown in this diagram. You can see here, and then we have some sort of a cylindrical surface, and it has a coating, and you are able to see the coating. There is some sort of a rupture of the coating. Some coating has come out from a surface. So, in that case, what will happen? The signal will vary, and it will not be smooth, and moreover we generally look at the signal difference, we do not look at the absolute signal, we look at mostly the signal difference as such. So, you can see here that in this zone we are getting some sort of different kind of signals. Now, this signal does not give as it is a thickness. So, we need to have understanding what is the meaning of this signal, is whether it is in so the amplitude wise, and if it is amplitudized, what is the correlation, and then can we have a linear correlation, or maybe they will have some sort of the logarithmic correlation, exponential correlation, that requires the science behind that. So, and however, most of the sensors which come, they are calibrated and then they are given directly in the dimensions. So, person or maybe even the company or factory which makes a sensor, they need to have a complete knowledge. And I have realized also that whenever this sensor, if you do not use for a couple of months, and when you want to reuse this sensor, you again require a recalibration, or time to time recalibration is required. Otherwise, this sensor do not give absolute value, basically they give relative value, and relative value keeps changing. So, that is why the recalibration is required every time, and then we can get a good reliable results from that point of view. So, now this is what has been mentioned. Now, another one important point is attenuation. If I am transmitting a wave from one place to the last place, there is a possibility that some sort of energy will be lost, and that energy loss is basically attenuation. So, I will be getting finally some other response. So, if I have a right calibration, everything will be accounted in that. If I do not have a right calibration, then I will not be able to account that, and I will be getting unnecessary misleading results. There may not be any fault at all, and I say, oh, there is a fault, that is why the mitigation is happening, or maybe there is some sort of attenuation is happening, or some sort of energy consumption is happening. It does not. Reason being that there is a material, and that whatever the media, if we change the media from air to liquid to the solid, naturally that this the ultrasonic wave which is passing, some sort of attenuation will change, the behavior will change. So, that is why we really require a recalibration every time, and that gives a good result. So, attenuation is what where the energy of the wave gradually decreases as it travels through the media, right. So, this is what I mentioned. If the surface from a top to bottom, it will have some sort of attenuation, and that need to be recalibrated. Either this calibration again will have some sort of range, maybe like this will be valid only from 1 to 3 mm. If you use a lesser than 1 mm, it will not be useful. It will lesser than or more than 3 mm, it will not be useful. So, every sensor will have some sort of lower limit and upper limit, and we should operate complete unit in that duration, or maybe that range only. We should not go say whatever the distance it can measure, the sensor can measure it. No, it is not necessary. So, we need to really look at what is the range, what is been given lower limit, what is been given upper limit, and we need to work according to that. Now, how do we really generate this kind of waves, electromagnetic ultrasonic waves? In this case, to generate ultrasonic wave, generally we use a piezoelectric the crystal. And what is a piezoelectric crystal? If we provide some sort of voltage to that crystal, it will vibrate, and that vibration is basically ultrasonic wave vibration. It will generate ultrasonic waves. So, we can generate ultrasonic waves. We know what will be the lower limit and what will be the upper limit. Of course, earlier what was mentioned as the 1 megahertz, now it has crossed, and then people are going with the gigahertz also. They say there is no upper limit as such. Now, another thing, as I say, that it goes through the media, there will be some sort of attenuation. So, we need to look at the calibration, we need to really look at that what kind of curve fit method has been utilized to get the results. So, those things are important. Once those things are done, then we can really predict the results. Of results can be related to the existing fault, or maybe even the material thickness. When we are talking about micron level coating thickness, that can be measured. If there is some sort of other fault, or maybe say some sort of a reorientation on the grain boundaries and all, that also can be done if we tune the surface, or maybe the sensors from that point of view. So, these are important things. Now, let us look at what are the different techniques to utilize this ultrasonic NDT. As we are seeing, the first technique as such is a transmission method, as I mentioned that in this is basically we use a transducers, two transducer, one is this side, other one is other side, and there is some sort of a material in between. So, that is why it has been written we use two transducers, one on each side of the substance. So, this is what has been shown is like a substance. So, one substance and then the one on this side and one on this side. However, we have shown two pieces just to differentiate. In one case there is no flaw, so there will be direct transmission. So, that this direct transmission has been shown with a green arrow. Now, when we have a flaw in this case, naturally that transmission will not be 100%, there will be partial transmission, and then the remaining they will be reflected back. So, here the other sensor which is a transducer which is receiving this signal need to be tuned to figure out what is really happening, and that is the transmission. In this case you can see the one case the amplitude is very high, almost most of the energy has been collected at the receiving end, while in the case of the two you can see that there is some sort of lesser value compared to this first one, and that is the reason being that the energy has been reflected back, or waves, these waves which were impinged or on striking against the crack, they have been reflected back. So, that magnitude has come down, and as I said again that these are the relative method, we do not have absolute method, we try to compare like healthy and unhealthy. So, we can say yeah, we are getting lesser energy in this case, this much amplitude. So, it is unhealthy compared to this one, right. So, we can just compare, we will not be able to give absolute value as such. So, it has been written the two transducer, as I say that we are discussing about the transmission method, and then this transducers are utilized one on each side. This is a substance has been mentioned. Now, transducers which we have been utilized working as a transmitter at one hand, and other hand it is acting as a receivers, right. So, one is sending this waves, ultrasonic wave, and other is a receiving end, and as which the transducer which is receiving, that can be connected to the display system or computer to the further calculation on that. So, now if I really explain this method, we say ultrasonic pulse passes through the material, it encounters the material interior obstacle, as this has been shown using this color and then the black color in this flaw here. So, material obstacle that can be a grain boundary, it can be a crack or fissure, it can be void, it can be inclusive. So, this void and inclusive can be treated as a 3D, and maybe the grain boundaries and fissure can be treated as a 2D. So, something like we have a linear kind of a thing, or we can maybe the linear in the sense thickness is negligible. So, I am assuming this is a 1D, and then this is a kind of 3D. So, we can really look at the both 1D or 3D in this case. Of course, 2D we are not considering these, assuming that the thickness will be almost negligible, or either it has a 1 dimension or it has a 3 dimension as such. Now, this is these hindrances cause interference in the pulse, because there is a transmission path that has been shown here, transmission something like that, and suddenly we are trying to bring some sort of hindrance. So, this path is getting cancelled as such. So, only the two arrows will be transmitting, and that has been shown in this figure. So, this is what we say that hindrance cause interference in the pulse, changing the characteristics. So, whatever we are receiving at the receiving end or by the transducer, that will be changed, and as in the captured and modified pulse is converted, or maybe getting different signals. So, it will be getting converted to electrical signals at the end of the receiving transducer, and this signal is then analyzed by ultrasonic flaw detector or maybe some sort of processing software. So, these are the essential, we really require unit which will generate it will generate ultrasonic waves. We required unit which will receive ultrasonic waves. We required a kind of processing unit which can really figure out how much was in and how much is out, to compare it and then figure out what is really happening. So, we really require a signal processing software, or we call it some sort of a ultrasonic flaw detector. So, these are the essential points. However, many times we do not really consider this, reason being we buy some equipment we directly put on our machine and we found some sort of results. As mentioned earlier, that if we really required valid results or good results, we need to really do good calibration also every time, or maybe say whenever there is a gap of couple of months, when again I am using the sensor, there should be calibration so that we get a results and the normal results are right results as such. And another thing it comes, now this crack has been shown something like this. Now if this crack has been like this or like this, and there is a possibility there will be multiple cracks, we do not get only single crack, and again there will be some sort of the sensor which has been used, naturally it will have some sort of limit. It cannot look at the complete thickness, complete circumference, complete area, complete volume. Naturally we need to change the sensor's location also. So at which location we are diagnosing, and that really required 1,000 sensors, or we required only 2 sensors, 3 sensors. So these points are important to be considered whenever we are studying this kind of the sense and the technique which really provide a good results. Either we know very well which is the most critical location and directly engaging sensor there, or we are doing some sort of scanning first to figure out what will be the really right location, and then we are using that, maybe say few location we thought these are the right location, and we engage the sensor, we get a results, and again go for the next iteration, which location will be the better and how do we move next. So again this is a iterative procedure. As I mentioned, there is a possibility there will be multi cracks, the faults. In the situation we really required more than one technique, so that we get a more or less comfortable results or reliable results or results which are matching with each other, and there is a minimum which is the deviation between the two techniques. Now that was a one transmission. Now a second technique is what we call as a pulse echo method, and this pulse echo method is basically reflection. What is in this case, we are using a sensor, only one transducer. It is really releasing this giving the rays and collecting back the rays also. So one sensor and it is doing the both the things. That is why we say the pulse echo method, which is a reflection method, uses an ultrasonic transducer to send a short burst of the short waves of the ultrasonic pulses into the sample material. Here I am using the word sample. Whatever the material we are testing, even though when we discuss about the DT and NDT, we say very clearly, in DT we make samples, in NDT we do not make samples. So here when I am using the word sample, it is basically material, it can be real product also, we can directly engage. So this sample does not mean that we have prepared a sample, here we are just testing the material, so that is why we use the word, but it is not that we have especially made the material for that purpose. Now coming to the how we generate, we use a piezoelectric crystal within this transducer, which will vibrate in response to electrical signal which has been given. That is what has been in response to the electrical signal, naturally producing that, and the transducer will give this waves, and then we get those waves, ultrasonic waves, that will really hit the imperfection or discontinuity, and whenever there is a discontinuity or maybe striking against discontinuity, some energy will be reflected, and that energy is what been collected. So one transducer, it has a piezoelectric actuator, or it will really whenever electrical signal is been given, it will really vibrate at a high frequency, it will really give ultrasonic waves, and ultrasonic waves will be released and then will be striking against a discontinuity, imperfection, reflecting back those waves, and then some whatever the partial portion or whatever comes back, that will be collected by the sensor. Now what is the advantage compared to transmission? We are using only one sensor, and then if there is no flow, this sensor does not get anything back. So we do not have unnecessary details available, we have only necessary detail which is really required, which is more unique than the meaningful, only those things will come. But here continuous phenomena cannot happen, naturally there will be some sort of gap, we are sending and then we are collecting back. So it has to be more like a pulse mode that we are sending, then waiting, and then maybe kind of some sort of delay time, and then we are getting the waves back and analyzing those. So, lesser equipment, but more software side, more on coding side has to be better and better compared to other methods. So, in this case we can say the same transducer that emitted initial pulse also detects a echoes, or maybe say that reflection, echo is a reflection. So, this method detects reflected waves and converts those waves into electrical signal. Again, everything is indirect, we are not able to measure anything direct, everything is indirect measurement, and we need to have a science, we need to have connection, and we need to have minimum to minimum noise. If the noise is not minimum, we will be getting very bad results also. So, this is what we conversion, energy conversion is again happening, and it will will provide to the device or to the software, or maybe there is some sort of a detector which can really detect it. So, this will be signal will be provided to ultrasonic defect detector. Now, this defect detector, we are using the word flaw detector, examines the reflected signals, and then by measuring its amplitude, it can be time of the flight, how much time it took, and it has come back, and then other relevant parameters which are really mathematically connected with each other, and then based on that it can really evaluate and then provide the characteristics of the flaw, about the how many faults are present, where the faults present, whether gives the location, and what will be the kind of size of the fault. It can be done, but again these are all idealistic situations. How much we are getting, because even it's little bit change in the surface roughness can spoil complete thing. So, we need to really, even though I am saying we do not really make the sample, but we make surfaces which needs to be examined, it need to be clean. If the surface has some sort of corrosion, some sort of rusting, I can't use this signal directly or maybe sensor directly. So, preparation of the surface is important, not a preparation of the sample which we do in a dust detector testing. So, please do not get confused, here we also prepare, we also clean, so that sensors can be attached to the surface properly. It is not that we do not attach the sensor, or maybe even there is a slightly gap, then again still we need to smoothen the surface, so that a discontinuity can be minimized, otherwise actual they will not be cracked, and our sensor will get all the noise which is related to the top surface. It may be because of surface roughness, maybe some sort of a dirt, maybe some sort of a soot formation on the surface. So, we will be getting all bad results. So, for to avoid that, we really require we require surface preparation. Now, one more thing which is coming, that we have used two different methods, but what about this ultrasonic waves? What kind of waves we are using? Of course, we say that high frequency, it should be more than 20 kilohertz, it should have a lesser than 1 gigahertz or maybe up to gigahertz, that is what we have done. But there are other waves also, and those are the something like a longitudinal waves, shear waves or surface waves. So, there are three different kind of waves. So, again even though there is we are discussing only one technique, that is ultrasonic technique. Ultrasonic technique has already two different kind of the sensing units and three different kind of the waves. So, itself is the big topic as such, and we are trying to give only overview in this course, so that we can really bridge, or we can build our course on this, that we in detail we are examining only one or two techniques, but more or less all the techniques will be similar, and then we are giving time to the various resources which are available, as most of the time we are getting from ASM handbook or ASTM handbooks. So, that is what we will be briefing. Now, as I say, the ultrasonic testing uses a variety of the waves. It can be a longitudinal wave, it can be shear wave, it can be surface waves, to investigate the surface and internal surface features also, or substance internal features. So, these are the important. So, I am just trying to give some sort of overview of this the wave. We say that we have a longitudinal wave, we have transverse wave, and we have a surface wave. It has been shown here the longitudinal wave, wherever there is a localization, there will be some sort of compression in a wave, some sort of change in the wavelength will occur, and if we are able to diagnose this, that also will give some sort of information what is really happening at the localized level. Now, coming to the transverse wave, mostly these waves are the perpendicular to the direction of the wave motion, while the longitudinal is along the line along the way of motion, while coming to the surface wave, they are combination of both, and that is why that they are able to generate more like a circular waves. So, it is along and it is a perpendicular, and that is why there is a circular wave. Now, what is the advantage, what is the disadvantage? In longitudinal waves, we use the word mostly as a primary waves, and sometimes we use the word a P wave, right. In this case, it travel parallel to the direction of the wave propagation. The advantage is that it can be passed through the solid, it can also be utilized in liquid, it can also be utilized in gases. So, it can utilize in all kind of media, solid, liquid and gases. Now, this is effective whenever there is a volumetric defect, and the defect has a volume, and one of the earlier slide I mentioned, it can be 1D defect or it can be 3D defect. Generally, we are not counting 2D defect. So, this will be good for the 3D defect, and that is what we call as a volumetric defect. And volumetric defect, as one of the example is a void. It can be have inclusions, maybe inclusions is the foreign material which is getting into that, or it can be have a crack which is much bigger in a size and it has a 3 dimension. So, basically anything which has a 3 dimension and which is a countable, maybe even at the micron level, that can be, and we need to use a longitudinal waves for that. Now, coming to the shear waves or S waves. So, first we mentioned here the P waves, and here we are saying the S waves. The P waves and S waves. In this case, the secondary wave, basically the these waves travel perpendicular to the direction of wave propagation, and that has been shown, wave propagation direction and the direction of the this transverse waves. In this case, these waves require solid medium only, we can't use in liquid medium, we can't use in the gas medium. So, propagation path is only in a solid waves, and they are really useful to find out the faults or maybe the flaws which are perpendicular to the wave path. So, where we are sending the wave something like that, and there is a perpendicular crack which cannot be diagnosed using the longitudinal wave, then in this case we require S wave. So, again this kind of knowledge is important. Now, coming to the last one, the surface wave, and this has been it was given by Rayleigh, that is why it has been utilized, and then in this case it gives both the combination of that. If we are not very clear, we can use this kind of waves, so that we get some sort of indication, and then we can move ahead with a more and more detailed analysis. So, we have 2 different methods to position the sensor, and then the transmission and receiver, and the one sensor transducer which can be used as a transmitter as well as receiver. So, naturally the associated software will change a lot, filtration system will change a lot. Now, coming to the waves, again every wave generation, and then we need to diagnose, again related to software or the unit will be different. So, that is why we say the different waves mode provides a valuable information about internal and surface condition of the materials. It can really enable effective inspection of the various configurations. Maybe we will highlight a few and maybe one case study on that. Now, question comes, how do I go ahead, what is the procedure? Now, that I believe that it will take almost 3 to 4 lectures if we really want to develop a complete software and maybe develop a complete relation. However, I just can say that creating an inspection process, particularly this kind of process as such, if it is a well established method, we can utilize as it is. But if you want to develop that, it will turn out to be complex task, because we really require in-depth technologies, and that to expertization related to those technologies also. And many times we want to really measure something like a nanometer thickness. it will be very difficult, reason being the noise will be very high. So, we really require a good filtration system, signal condition and knowledge in that case also. So, parts that are too small, too thin, too irregular in shape, or maybe totally non-homogeneous, or maybe the parts we having numerous defects or cracks, that cannot be really measured in this case, and then we will have a limitation. Another thing I mentioned very clearly, that we really require a cleaning. So, cleaning and scrapping off any loose debris, or maybe say the foreign material, or maybe dust, or maybe oil, then they need to be removed, otherwise we will not be able to get a good results as such. So, thumb rule is that if the thicknesses are too small, please do not use this. If there is some sort of dirty surface, please clean it, then only use it. And then we already have learned about the 2 sensor system and then 3 waves. So, their overall price of this equipment varies a lot. So, we say depends on what is really requirement, what kind of faults we want to check. Of course, we should have a universal machine, but that will turn out to be very costly. And then only one good procedure point I can suggest versus the cleaning. Second is that the calibration, and we should use some sort of reference materials, because whenever we buy anything, the company gives one sort of reference, and then calibration has to be established against that. So, if we have some sort of references, a reference standard, that should be utilized in a proper way. Another thing comes even how to differentiate the signals, because I will be getting a number of signals on the various location. Even if I change a sensor orientation, I will get quite different results. So, we need to have established chart and then complete system to say that how do we go ahead. So, one case study we will say also that how do we really check these signal from the faulty side, or maybe from healthy side, and how do we compare. As I mentioned, that these signals are not absolute, and we should not rely on absolute signals, it should be only relative. So, what are the important consideration from procedure point of view? First is that we need to have a clean surface. Second thing is that the right sensor, and maybe whatever the unit we are using, it should have established and then the filtration condition the unit, so that then the signals maybe signal to noise ratio is very high. And another one is that we should choose the right references also. We should not go ahead with the very thin surfaces which are giving too much noise, which those things are important. So, if whenever we buy any sensor, we should look at those units, that what is the really range, whether range is in appropriate manner or not. As I mentioned, that these sensors, they do not come in a complete range, they will have some sort of narrow range, because the calibration constant remain well within limit in that range only. This whatever the calibration constant they give, it will not be and we say that available for the complete range from 20 kilohertz to 200 kilohertz or 1 gigahertz. So, there will be a sensor, and then the sensor will have a sensor related unit also will have some sort of a upper limit and lower limit, which should operate only on those units. And we should also look at what is the acceptable limit or permissible limit. Those points are really required whenever we are trying to utilize this kind of technique. So, I will just try to highlight one of the case study. As I mentioned, we will try to look at one case study. So, in this case particularly, this case study has been picked up from literature, and this was published in 2020. And this case study is basically on the wind turbine blades, and then you can see that the two wind turbine blades, one blade is here, another one is here been given here, and then it has been written also this blade is damaged, this blade is healthy. So, whenever the lab tests are done, most of the time intentionally the damage is created, and then we know the damage is there, whether our sensor, our unit is able to give right results or not. And then we also know, we already have mentioned that this kind of transducer can be utilized, and like in this case in plate, we know that if the energy is going completely through and through, this is a complete transmission, while if there is some sort of delamination or some sort of irregularity, then it will really reflect back. So, that sensor positions will change, and this has been shown when there is no flaw at all, initial way is equal to this. Now, if there is a flaw, now if I am checking the echo, that this signal comes very clearly, that indicates that the signal has come down or reduced in this case, while if you go for the other side it has another case. So, there are two different methods, and whichever method we can go we want to utilize, that can be done. Well, in this case what they have done, they first scan through the frequency domain also, and then they started from 20 kilohertz and then they went up to the 100 kilohertz. Which frequency is really giving a better results for this what we say that the WTB1 and WTB2, and then they found that 50 kilohertz signal is giving a better signal to the noise ratio, or maybe the superior signal to noise ratio compared to the range which has been utilized from 20 to 100 kilohertz, and then scan through the gap of the 5 kilohertz. Maybe that they have done experiment at 20, then 25, then 30, the 35, 40, and found the best results, superior result at the 50 kilohertz. So, this is one of the important parameter. Whenever we want to test, we need to scan through frequency range, which frequency range is really giving good results. Again, maybe one setup maybe 50 kilohertz, but if I change kind of the equipment, I change the dimension, quite possible 50 kilohertz may not be the superior results. Again, we need to scan through and then figure out what is the really right thing. Now, another thing is that because this unit is a very big, you can see that the widthness, the thickness, or maybe say width is much smaller compared to the length. Naturally, one sensor cannot be utilized. So, that is why they selected around 38 positions, and then sensor location at the gap of 100 mm. So, maybe one it has been kept at 200 mm, then 300 mm, then 400 mm, then 500 mm, then 600 mm. So, something like that, and then they found defects at the location A, location B and location C, and you can see this itself is the dimension itself is varying from tip, or maybe say one surface on the one end is roughly 2300, and then other one is a 2800, and last one is a 3500. Now, this is just a thinking that these are the defects A, B, C that has been shown, and then that is what has been mentioned here, that these are the disbond between this one. And now, what they are trying to look at, again there may be numerous fault, may not be one, but naturally question comes which kind of fault we are trying to diagnose, and then they try to figure out what will be the dislocation or disbond between honeycomb structure whatever they are using and the final skin. And then another important thing is that honeycomb structure starts at the lesser after certain duration, or maybe say after certain length. At the beginning itself honeycomb structure is not starting. So, that again if we try to figure out some fault in this zone may not be useful at all. Reason being, they do not want that, they were looking at only the delamination between this honeycomb structure or support system and top skin. So, these are the important aspect whenever we are trying to go ahead with the diagnosis, or we are using the testing method, and what is really important we look at only those. So, if I say that what they did, they use a two structurally identified honeycomb cord wire, wide and thin we say the wind turbine blades. So, in short we say WTB, and those two units were identical, only the difference was that one was healthy, other had some sort of delamination, maybe say some sort of damage other honeycomb structure as well as the top skin as such. So, there was some sort of disbond between these two. Now, when they connected the transducer at a different location, naturally all the sensors were on the outer surface, otherwise it will not be NDT, it will become a DT. So, they look at only the outer surface. Of course, I can go at the other side of that, but again it will be outer surface only. So, we did not fit any sensor within or maybe say after damaging the surface. So, either the top surface or the bottom surface, in this case they have done everything on the top surface. Now, they are housing the top surface, naturally we have a very long length, and that is why they have put 30, they locate the 38 locations, and then they got a response for that. Now, when they are getting response at the different location, let us look at the location 200 and location 300, or maybe say location 100 and location 2. So, they try to figure out what is the difference between two signals. So, that is what they use a technique autocorrelation. If the autocorrelation between the place 1 and place 2 is very good, that means there is no crack in between. That means, suppose I say that the signals were collected at 100 mm and signals were collected at the 200 mm, and then I want to really relate these two signals, and there is a perfect autocorrelation between the signals, that whatever we got as signals at the 100 mm and whatever we got a signal at the 200 mm, they are more or less same. That means there is no crack, there is no discontinuity, there is no fault. That is what they try to utilize, and if there is some sort of the difference coming in autocorrelation factor, one the healthy gives a very good autocorrelation, and bad or unhealthy or damaged one gives a very bad correlation. Something the correlation factor is a 50 when it is a healthy, and the correlation factor is only 2 when it is unhealthy. Naturally, we will know there is something in between this. So, maybe 2300 to 2400 there is some fault. So, that is what the technique has been utilized, and this has to vary based on the person's thinking, and then what they, it can be 50 also, it can be 150 instead of that whatever they selected, the gap between the two signals, or maybe the two location 100 mm, but you can think about 150, okay, can was 350, and then basically this is a iterative procedure, and we start with maybe say 8 location, and after that we can refine, and maybe we find that some defect is between 500 to 1000, and I want to really modify, and I want to go for the 8 location only between 500 to 1000. So, this is a iterative procedure, and it can be done from that point of view. So, what I can say, the healthy the WTB will have a high degree of correlation whatever the signal we are choosing, while coming to the because of the delamination in defect will reduce the correlation factor, and then it will be corresponding to the whatever the defect it has. So, what they got, I am trying to show the results to you. In this case, you can see there is a figure 1 and there is a figure 2. And figure 1, all are the correlation A, B, C, D all, and then they have given the location. As I mentioned, they collected the signal and they tried to figure out correlation at various signals. So, they found a correlation whatever they achieve at the 200 and whatever they achieve at the 300. So, correlation factor. Similarly, in the B they have shown a correlation between at whatever signal they got at 700 and what the signal they got at the 800. And another case they have shown a signal the 2300, signal at the 2400. And last one the D has been shown the signal at the 2900 and 3000. So, you can find that there is a difference of 100 in each reading, right, and then correlation has been established. Now, if you look at the correlation, this high value is important. Now, they could achieve a very high value, almost 300 in the case of the A. So, whatever the signal they got at the 200 and whatever the signal they got 300, correlation is very high. Now, coming to the B, they found a far better correlation compared to A. Now, this is again a kind of correlation is established almost double the compared to A. Now, this can be the much more steadier signals, or maybe because of the geometry, that is a possible. However, if I get a similar signal in the damaged one, that is a 2, then I will say there is a we are not relating to this at all. Whatever they got, we do not have to really go into this. So, now in the 2, which is the damaged WTB, in this case you can see A, they got almost same signal, whatever they were getting 200 and something, they are getting almost same signal. Now, coming to the B, they are also getting a somewhat the same result, whatever the maximum value, and then it is they are getting similar kind of the values. So, maybe the very little difference, but is not noticeable as such. It may be the slightly lesser in A and B, but not very significant, and then we are not able to look at we do not have to really worry about this, we do not have to worry about this, we do not have to worry about this, we do not have to worry about this. So, this is fine. Coming to the C, what they find that there is a drop. There is a drop in this case, like in this case suppose there is a 500 and here they are getting only 45 something. So, there is a huge drop, and now this huge drop may occur because of the attenuation also. You look at that, they collect a signal somewhere 700, 800 and now they are getting signal at here and then the 2300 to 2004. Now, there is a possibility the attenuation should not be accounted that much because we are counting between the signal of 2300 to 2400 also, right. So, this is only 100 gap, while in this case also 100 gap, we should get the same signal. So, again they have highlighted that because there is a possibility of internal some other defects, we are not worrying about this also. Well, now if coming to the damaged one, they got instead of 45, they are getting this correlation only the 15. So, that is why they are able to see that there is some sort of difference between this signal that is significant. While coming to the further D side, and then the correlation in this case is roughly the 25 in this case max value, while here there is a 4 to 5. So, there is a big deviation over here. So, this is a noticeable. Now, once we get this, we need to repeat the results. It is not that we need to say okay, this is the results, we will finalize it. Though quite possible we have got some indication that there is something wrong in this range 2300 to 400 to even the 2900 to 3000, there is something and we need to look at what kind of fault we can reproduce it also. So, these are the important, and as I mentioned that is a kind of iteration we need to really look at those. So, what I can say that they obtained a signal in the 200 to 300 range, which shows a lot of consistency with each other, high correlation factor as it was shown in figure 1a. And similarly outcome they show the correlation when they collected the data at maybe the location 700 and 800 also, which was shown in figure in 1b also. So, this area appear like there is no as such problem, and then whatever the variation is happening because of the skin which is really in the getting deposited at the honeycomb structure, and that was before kind of the honeycomb structure really started, right. So, this signal they were not worried much. Now, coming to the figure 1c, what we showed that there is some sort of inconsistency and energy loss at the level, as I say the correlation varying from the 500 to directly 50 or 45 something like that. So, these defects may be there. Now, they say that there is a possibility the elastic wave energy is getting dissipated in the system. However, they wanted to compare 1c and 2c. So, that there is a huge difference between the signal, and that shows very clearly that there is a delamination. Now, figure coming to the 2D, that shows a very it's a very weak correlation. Now, only the correlation factor is something like 5. So, there is a weak correlation which attributes that there is an inherent some sort of a flaw also, or maybe the sort of the dissipate when there is the delamination happen after the signal is not really getting transmitted properly, and this is the delamination is a very prominently looked at that, and that requires little more iteration and then come up with a far better results. However, in this case what they intended and then they created a fault. So, they knew each and everything well in advance, but in reality we will not know about this. So, that is why we require many more iteration to come up with the right results. So, that is why this kind of techniques are a bit costlier compared to the visual examination, and then we require more iteration, and finally we need to judge based on visual examination. So, visual examination inherently will be there in almost all the techniques, and then when we use this kind of techniques, we need to do like in a good we need to have a good knowledge about the technique, and we should have a good brainstorming sessions also, how to improve the results, how to locate complete thing. We should not immediately jump to the conclusion. Quite possible we are getting good results, but we may get a better results if we go for the more iterations also. Now, just thinking about the defects, which no, we say that delamination was one, separation between two surfaces is one kind of defect, but question comes what are other kind of defects. So, there is a big category of the defects and it has been established in the literature also. I am just trying to show in this slide some sort of a type of the defects in this case. We say there is a possibility of the defect which is dividing the surfaces. So, there is a linear the transverse crack and there is a longitudinal crack, and you can see that this crack also has a depth. So, whenever we are saying that surface breaking linear the crack, that means it has some sort of depth. So, that is why we say that liquid test can be done or magnetic test can be done on this. So, that particles can go inside, a dye can go inside and figure out what kind of crack it has. So, most of the surface cracks I will not go ahead with the UT test as such, maybe we will go with some sort of a liquid test or on the magnetic test, so that we get a better results. Now, another thing is something like a surface breaking the volumetric cracks, and then you can see the depth is there in this case. The volume is there, that means that there is an area on that which is visible and there will be depth in this case. So, these are the another case. So, that this is the 1, this is a 2, this is a kind of thing again from with on the cracks which are appearing on the surface. I can use VT and maybe say liquid test on the magnetic test because those are far cheaper compared to the our other tests also. Now, coming to the subsurface where the UT kind of the test will be important, because we are not able to look at the defects. So, MT or maybe even the MT can be utilized, the magnetic particle MP can be utilized as such, but in this situation better results will come from this kind of a UT test as such. So, we say the near surface linear and normal to the surface. So, there is a surface and then there is a perpendicular to this one, other one is that parallel to surface. So, one is a perpendicular to surface, other one is a parallel to surface. Of course, the crack may also happen like this or maybe like this also. So, orientation can happen, that is why we require better techniques. However, in this case because it is below the surface not visible to us, so we really require a good techniques in this case. So, this is maybe the third kind of a crack, this can be 4 type of crack. Now, coming to the subsurface volumetric crack also is a big kind of volume, kind of the void below the surface, that is a possibility. Now, coming to the near surface, this is a subsurface. It is not very near to surface, but it is below the surface, while in this case it is a kind of a near volumetric near surface volumetric crack. It can be kind of pores just below the surface, and then maybe and then after a few cycles or maybe the 30 cycles it may become a big pit also. So, this can be again can be diagnosed utilizing the better techniques. So, if I want to really tell in my words, I will say that we have basically 6 kind of the cracks. We say the linear flaw, that is what has been shown. Linear flaw that penetrates underlying this material, maybe there is a vertical depth. If there is only the kind of a scratch, it does not have a depth, then we do not have to worry that much. Okay, and then well, it has some sort of a crack, and maybe say that dividing the surface, right. So, linear flaw that penetrate underlying the material from a surface is to be said as something like a surface breaking linear flaw. Such flaw can take form of the fracture in if we allow for the longer duration, or maybe we need to mitigate, we need to really avoid the catastrophic failure. So, we need to really immediately take measures. So, that is why that this kind of flaw identification is essential for us, and most of the time this flaw can cause a fracture. We have obtained this kind of flaw mostly the joints, or maybe wherever there is a shrinkage, there is some sort of a lamination, or maybe then there is some sort of leak or some sort of a deep crack as such. So, then the deep and big crack as such. So, such cracks basically make the material weak, and that is why the ASTM has a complete norm is a 165 for more information. So, if you are interested, you can look at the ASTM E165 for more information related to that. Now, second what we mentioned about surface breaking volumetric fault. So, the fault which is exposed to the surface, and it is a deep also, it has a depth. So, that is why we are using the word a surface breaking volumetric fault, and these are the defects that extend over the noticeable depth, maybe say we can measure the depth. These are not a kind of a scratch or maybe the biggest scratch, they are having some sort of depth. So, and the flaw that extend beneath the surface can include something like holes also, maybe initially the crack was only there and there was number of holes and then maybe get connected with, or maybe there are some sort of inclusions also. So, then if these are the kind of the common cracks or maybe common defect, again ASTM E547 standard really clarifies or provides more detail about this kind of defects. So, these are the important. Now, another one what we look at the near surface linear and normal to the surface. So, one is a near surface just below the surface. So, we cannot utilize normal first three technique visual examination, liquid penetration test or magnetic particle test, we cannot be utilized as such for the reliable sources. So, we really require a costly or maybe say sophisticated techniques. So, we say the near surface linear and normal to surface defects are the results of the metal maybe the material inhomogeneity or some sort of residual stresses which come, or maybe saying the many times the excessive metal mechanical loading has happened, or maybe the tensile stress has happened, that is why it has created some sort of defects there, or maybe some sort of environmental conditions. So, quite possible sometime we may get some crack and the hydrogen embrittlement happen, as I mentioned in one of our earlier lecture. So, this is important. Now, other than that was a near surface linear and parallel crack. So, one is a normal crack, other one is a parallel to surface. Mostly that kind of cracks are developed because of the manufacturing type or machining time or the grinding type. So, those are the manufacturing defects, and if we are able to figure out beginning itself, we can really change the manufacturing processes, we can really make a better surface or the better manufacturing processes for that kind of units. So, another what we have studied something like a near surface volumetric defect. So, it is again near on the surface, it is not on the surface. Again we require costly techniques to really find out. So, these refer to the nonlinear, and then as I say 3-dimensional flaw, because wherever the volume comes there will be 3D will be coming as such. So, 3-dimensional flaws or imperfection, they are again found closer to the surface. Naturally, it will be very important for us to find out what is really happening. Now, another what we use a term something like a subsurface volumetric defect. It can be referred to the flaw in a material that goes below the surface. It is not near surface, it is below the surface, and this is something like a hidden faults, and then it can be voids, and then it can be the inclusions, it can be porosity, it can be big flaws, and most of the time it happens in a casting kind of a units, or maybe the manufacturing by casting as such. So, we need to really look at the processes of manufacturing process, need to improve that. Sometime if it is not really in the manufacturing defects, then we can avoid, we say okay, then we do not have to look at that. Only if this kind of faults are found and we find that we can tune the manufacturing process, we should go ahead. If it is not really going to affect the material strength immediately, unless those voids are really, we have associated units or maybe mechanism which will expand that fault and then the fault to the surface. So, that will not be that kind of important importance will be given. Now, another thing is what we say that whatever this defect, these are already available in the ASTM standards. We can look at those kind of the standards and then figure out what kind of faults, what will be the possibility of those kind of faults in our unit, and based on that we can choose a technique. Now, I am trying to bring to my last slide. We say that we will be studying the few techniques, but what we have covered something like a visual technique, and what we have covered today is in this lecture is something like ultrasonic technique. Now, when really we have so many techniques available, the question comes which technique I will be selecting. So, we will be covering that in a separate lecture, but I am just trying to give overview what we have studied something, and this is the one crack, this is on surface. So, that is what we use the word surface breaking linear crack. Then we studied something like a surface breaking volumetric crack, something on here. The another one is the near surface linear and normal to the crack. So, that has been shown over here. And then last one is in this fourth is another near surface linear and parallel to the surface. So, these are the 1D, this is a 3D and this is a 1D, this is another 1D as such. Now, near surface volumetric, and that has been shown in this case. So, this is the 3D and then finally subsurface 3D in this case. So, we have just given some sort of a ranking to the different kind of processes, testing processes. So, I am just trying to mention here. Now, here we have also used A and B. What is the meaning of A and B process? We say this can be utilized only for a ferromagnetic material. So, magnetic particle or AMBI test can be utilized only for ferromagnetic particles. Then coming to the B eddy current based, we can say this is only useful for the conducting materials. So, if we have a material which is not ferromagnetic, I can really remove this unit completely. A material which is non-conducting or cannot conduct it, I need to remove this technique, right. So, this is depending on the what kind of material we are using, and then again what kind of defects we are thinking in that. So, based on the defects we have given the ranking, and the ranking say that it will not detect, 0 means it will not be useful at all, and 1 is not well suited as such. 2 I can say average, the kind of can be selected if the available sources, or I do not have a costly machine available and this is based on the availability. Third one is that ideal application and maybe this machine should be utilized. Now, coming to this surface breaking linear in the defect, we say visual can be utilized, but I am not giving very high marks, it need to be associated with other. Now, similarly in this case near surface, as I mentioned, maybe on the surface what is visible, I will not give high marks to the ultrasonic at all. So, anything which is coming will be on the surface, I will not give the marks as such. And then coming to the surface, in this case this is a much more clearly visible, we can find out. However, I can even give better marks to the visual compared to the ultrasonic, because ultrasonic is slightly costlier compared to the visual. So, I will not give. Now, below the surface nothing will work for the visual, right. So, this is important. Another one is that this is a perpendicular. So, I like to this ultrasonic may not give very good results. So, for that purpose I am giving 1 only, not a 3. So, if it is having more volume and then maybe not very thin, which is perpendicular, either I should use some other direction or some oblique direction. In the normal direction I will not go ahead with ultrasonic equal to 3. So, this is what I am trying to show. However, in this case a reasonable volume is there and I can use ultrasonic technique as such. However, if I consider the cost, I will not give very high rank. So, depends on the kind of the first, this ranking is given only based on the type of the cracks. There similarly there will be number of other features also whenever we want to select the real right process. Here we have mentioned only material based on the ferromagnetic and conductive material and type of the cracks. So, similar feature, there will be number of other features we need to account which method, which technique will be more useful for our purpose. So, that is what our aim of this course. So, communicate right method so that all the students they take a right decision and then give overall cost economic solution to the society. Thank you for your attention.